Hi everyone, welcome to the fourth lecture on this module on smart building sensors. We are actually in the 11th module and we are discussing these sensors which are helpful in designing a building in a smart way or which make a building smarter. Okay? This is a course on microsensors and nanosensors. In the previous class, we have finished our discussion on air velocity sensor. If we see in this module, we have been discussing about the sensors for the purpose of smart buildings, and we have discussed the occupancy sensors, and we are discussing right now the building environmental sensors, right. We have talked about temperature sensors, then humidity sensors, air velocity sensors, and we thought that we will talk about photometric sensors in today's class. Okay, we will see some other type of sensors also, which is essential part of any smart building. Okay, so let us try to understand these photometric sensors, because till now we have not talked about these kind of sensors in our course. Okay. The photometric sensor, as the name suggests, it detects the light intensity and convert it into a electrical signal. That is what we have seen the definition of sensor. So, this photometric kind of sensor will detect light intensity and convert it into a electrical signal which can be readable, right. The optimal control of the lighting system with a photometric sensor significantly reduces electrical energy consumption while maintaining the visual comfort. Okay. Say for example, if you are doing some work in your drawing room and you want to move to say your dining area. Okay. So at that moment, what you want that the light in your drawing room should be dimmed, or at least or it should be switched off. Okay, and automatically when you move to your living area or say dining area, the light should glow up there, right. So this is what you say demand of the occupant who is occupying this smart building area. Okay. So this kind of thing can be fulfilled using this photometric sensor, which gives a sense of light intensity, and with the help of other control system, these things can be done. Okay. These sensors typically detect light in the visible spectrum in the range of mostly 360 nanometer to around 800 nanometer. The major concern of these photometric sensors are their placement. We will see one example that how the placement of these sensors is very crucial in a case of smart building. Okay. Let us try to understand this photometric sensor from the perspective of a sensor engineer. Okay. These sensors are based on the basic physics behind it is the simple photoelectric effect. So the light is incident on a material. Okay. And it generates some charge carriers. Okay, the ejection of electron and sensing that. Okay, this photometric sensor mostly are based on this particular effect. Okay, and depending on what you are using to detect this generated charge. Okay, you can have multiple type of photometric sensor, like you can simply use a photodiode. Okay, you can use phototransistors. Okay, simple light depending resistors LDRs can be used for this application, and for advanced chip kind of devices you have CMOS light sensors. Okay, of course each one is having their own advantages and disadvantages. Say for example, using a photodiode kind of device gives you very fast response and the noise levels are pretty low. However, with the phototransistor, although you have a better gain, but then these devices are slower as compared to the photodiodes. Okay, photodiodes are in fact they are two terminal devices and of course have faster response as compared to this phototransistor. Okay, then this light dependent resistors LDRs are very simple devices and very cost effective tool for this kind of application, and the CMOS light sensor of course require a kind of fabrication steps. Okay, however, they can be used for high end applications like for digital cameras and other applications. Okay. Now, as I have already defined a photometric sensor, now let us see a photometric sensor which is based on a photodiode. Okay. So, a photodiode based photometric sensor is again a light detecting device that uses a photodiode to to measure light intensity. We are discussing this photodiode based photometric sensor. We may not have time to discuss on phototransistor based device or a LDR based photometric sensor, but the essence of all these sensors, all these photometric sensors remain same. Okay, so once you understand this photodiode based photometric sensor, I think your job to understand the other sensors become very easy. Okay, photodiodes, if you do not know, are semiconductor PN junction diode that generate an electrical current which is proportional to the light or the photons they absorb. Okay, so as the name is diodes, maybe a photodiode, it's a PN junction device. Okay, so PN junction I think is clear to all of us. What is a PN junction? If you are not aware about a PN junction, you can read some semiconductor physics book or semiconductor device book. In this course also, I think I have talked at certain point about these PN junctions. Okay, so as the name suggests, these photodiodes are usually based on a PN junction. Okay, it functions as a light sensor by converting the incident photon on certain area of a PN junction into a electrical current. Okay, there can be multiple type of photodiodes. PN, I am just giving one example. Okay, it's a simple structure, that's why it is very popular, but other kind of photodiodes are also possible, like for example a pin photodiode. Okay, it has, along with a P and N junction, it has an intrinsic layer in between. So this intrinsic layer works like to enhance the sensitivity and response speed of this simple PN junction photodiodes. Then you have avalanche photodiodes as well as Schottky photodiode. Okay, the avalanche photodiodes have higher sensitivity and this Schottky photodiodes have faster response and mostly are confined to high frequency applications. Okay, so in this topic we will confine ourselves to a simple PN photodiode. Okay, so once we understand this, I think understanding other photodiodes will be not that difficult. Okay, so we all are aware about a PN junction. Okay, so in a simple PN junction you have a P type semiconductor and a N type semiconductor forming a metallurgical junction, right. For this kind of application, usually we require this particular area, we call it a depletion layer or depletion area. This is the requirement, a larger depletion area is required for this kind of application. Okay, so the junction between a P and N semiconductor is made as large as possible and as shallow as possible to maximize the light absorption. So basically the idea is the light will fall in this area or at least near to this area. Okay, this photodiode can have two different operating modes. One is photovoltaic mode where we call it no bias mode, and you have another mode which is a photoconductive mode or the reverse bias mode. So mostly in the photometric application, these photodiodes are working in a reverse bias condition. Okay, so the photodiodes basically operates in this case in a reverse bias mode where it is more sensitive and has a faster response time. Okay, what happen in the reverse bias condition, like you have a P type and N type semiconductors, and for a reverse bias condition the P side of this diode is connected to a negative of the battery and the N side is connected to the positive terminal of the battery, right. This is how you make your diode in a reverse bias condition. Okay, so what will happen in this reverse bias condition is this depletion area will widen. Okay, this will widen. Okay, now in this depletion area you have say this is the depletion area and this was my P side, right? And this was my N side. Okay. When it broadens, when this depletion region actually broadens, okay, it will have effectively more area to interact with the photons. As I have told you that the interaction of the photon and the junction is a requirement for a photodiode operation. All right. So, what happens when you have a semiconductor? You have a valence band and a conduction band. I think this is a very basic thing to know for a semiconductor. Okay. Now, you have all this electron in the valence band initially. I am not considering any electron due to thermal interaction. Okay. When a photon falls on it, some electron will absorb that energy, okay, and get excited to reach in this conduction band, right. Now, consider that a electron here or somewhere here absorb this energy, okay, and it starts moving. Okay. In that case, it will be lost very soon, right, and there will be no current flow at all because of it. Okay. Right. However, when electron near to this depletion region absorb this, there will be good amount of time before it actually combine or before it actually see any other hole to get combined or to get recombined. Okay. So, you have enough time for this electron to constitute a current. Okay. And that is why from the beginning I am telling that the interaction of the photon is maximum at the junction, not in these areas. Fine. So, the depletion region at the p-n junction widen in case of the reverse bias condition, and this will minimize the dark current. Dark current is when there was no voltage, there was certain current still flowing. Okay. So, you do not want very high dark current. So, it will minimize the dark current. However, the sensitivity will be maximized. Okay. So, when light is incident on the junction, photons are absorbed in or near the depletion region. Energy from the photon generates electron hole pair. The built-in electric field drives electron towards the N region and hole towards the P region, which results in a photocurrent which is proportional to the intensity of the light. Okay. This current is then used to quantify the light intensity, making the sensor useful for photometric applications. Okay. This involves the measurement of the visual light levels, anything from 360 to 800 nanometer. Okay. Now, there is a certain level of complication over here. Okay. We know that the photodiode measures the irradiance. Okay. Irradiance is the radiant flux per unit area, but what we are looking is for the photometric sensing, okay, which measures the luminous flux or flux. So, if you are not aware about the radiant flux or luminous flux, let us have a quick definition of them so that we understand that what is the role of actually the photometric sensor and why the output of the photodiode is not sufficient to be called as a photometric sensor. Okay. So, let us first define the irradiance, which is the output of a photodiode. So, irradiance is the power of light per unit area. This is, I am talking in terms of light. It can be say electromagnetic radiation also. Okay, so the same definition can be applied for the electromagnetic radiations also, but then the wave will be the electromagnetic radiations. Okay, so the irradiance is the power of the light per unit area, and it is measured in watt per square meter. Okay, so the unit is watt per meter square, and this is what exactly is given by the photodiodes. Okay, so this is the output of a photodiode, right. Then there is a term that I have just used, is the luminous flux. Okay, this luminous flux is the measure of the total amount of visible light emitted by the source, taking into account the human's eye sensitivity to different wavelengths. Okay, so this consider the human's eye, and this is what is required for the smart building case. Okay, so luminous flux is what we are more interested. Okay, and it is measured in lumens, right. Then another thing which is of our interest is the illuminance. Okay, so this is measured in lux and is a measure of luminous flux density. Okay, specifically how much this luminous flux falls on a particular surface area, and this is the thing this photometric sensor is all about. Okay, so this is measured in lumens per square meter, or this lumens per meter square is also known as lux. Okay, so this is what luminous flux and the lux are two things which is of our interest, but it is not directly given by the photodiodes. Okay, so a photodiode's output current is proportional to the incident radiant power, which is the irradiance, right. So it doesn't inherently account for the human's eye spectral sensitivity, because if it takes into that consideration, it should give the output in terms of luminous flux, right. So what could be the solution? What could be the way by which we can get output in terms of the luminous flux, or in terms of illuminance, which has a unit of lux, right. So the way people has come up for the solution is filtering and then calibration. Okay, so a filter, optical filter, is placed in front of the photodiode to selectively block or attenuate wavelengths outside the visible spectrum, because that is not being considered by the human eye. Okay, and then reduce wavelengths where the photodiode is more sensitive than the human eye. All right, then we have to do is the calibration. So the filtered photodiode output is then calibrated using a known light source with a known luminous flux. Okay, then this calibration process establishes a relationship between the photodiode's output current, which of course with the corresponding illuminance in lux. Okay, so that is how using a filter and a calibration technique, you can use the photodiode as a sensing element for this photometric application. Okay, similarly you can think of for a phototransistor as well as for the RTDs. Okay, then we have also talked about another kind of photometric sensor, which is based on CMOS light sensors. So CMOS light sensors also utilize the photodiode, but then fabricated using a silicon chip by the CMOS technology. So CMOS photodiode senses light and generate current in the very similar fashion that what it was doing for a photodiode based sensor. Okay, then the other thing that is essential here is to use a transimpedance amplifier, which converts this current output from the photodiode into a voltage. Okay, then this signal is processed by the ADC, and this gives the digital lux value. Okay, the output used in a real time lighting control system can be made using this kind of setup, and if you integrate it with a microcontroller, it can take decision that when to count the occupant, or when to not count, or for any other application that you want. Okay, so like dimming the light, or glowing the light, or switching on the light, or something else. Okay, For all these applications actually, whatever I have been talking, the placement of these sensors are very important, where these photometric sensors are placed. Okay, so that remains a challenge for the designers and the engineers. Okay, say for example, if this sensor is placed near to the window, then what it will do is it will dim the artificial light, because in the daylight sunlight is available. So, it will dim the other light inside. Okay. However, if the occupant stay say a bit far from the window, he or she may feel unsatisfactorily because there is no natural light. So the dimming may not work. So that is why I am mentioning again and again that the placement of this photometric sensor remains a challenge. Okay. So, if I talk about average home or average office, the average illuminance value in general building is about 500 lux in the occupied region, and in the unoccupied region it is around 300 lux. Accordingly, you can tune your photometric sensor. Okay. So, these photometric sensors are very much essential for the comfort and energy saving inside a smart building. If you remember the first lecture of this module 11, we have talked that the efficiency of energy saving of these buildings enhance by using the smart sensors inside this building, and this is one of the important sensor which is helping in the energy saving. Okay. Another kind of sensor which is required for smart building is the gas sensors. We have talked about gas sensor in module 5 in more detail, specifically the third lecture and beyond, where actually our discussion on gas sensors. Okay. So, we have talked there can be various transduction techniques for developing these gas sensors. It can be a simple resistive device where the resistance of the sensing layer, we call it receptor. If you remember, the receptor changes in presence of certain toxic gas. Okay. So it actually the gas molecules actually interact with the sensing layer by exchange of electron using the oxygen layer which is adsorbed on the surface of this sensing layer, right. So this was one way. We have also seen that these gas sensors can be capacitive device, can be made like a capacitive device also, where the principle remains based on change in the capacitance. You have different optical gas sensors which works on reflection, absorption, interferometers, fluorescence, change in refractive index, change in the optical path length, and etc. Okay. Then the gravimetric gas sensors were based on change in mass. We have piezoelectric as well as other kind of devices working for that. Okay. We have electrochemical sensors where change in EMF or electrical current is measured. Then we have FETs which works on change in the work function or change in the channel current and measuring that particular change. Okay. So, we have covered that in more detail, and all these sensors that we have discussed in module 5 can be utilized for this smart building applications targeting different gases which are very relevant to the indoor ambient. So, some of the gases which are relevant to the indoor ambient are carbon dioxide and carbon monoxide gases, then certain fuels like in the form of methane, in the form of butane or other hydrocarbon. Okay. You have ammonia getting generated inside the smart buildings. So, it has to be detected and has to be controlled. Okay. Then hydrogen sulfide is another gas which can cause a lot of discomfort and can be toxic at higher levels. So, these kind of gases has to be targeted for smart building applications. Then VOCs which remains the utmost priority for detection in the gas sensing area, and of course, for better comfort the oxygen has to be monitored, right. So, carbon monoxide and carbon dioxide has to do with the safety monitoring for avoiding any poisoning, as well as this carbon dioxide it helps in optimizing the HVAC for ventilation and comfort. Okay. Then for combustible gases like for methane as well as for butane, it helps in detecting gas leaks and prevent any kind of explosion. Okay. Hydrogen sulfide is important if you are dealing with waste management in a smart building. This is very much essential. Okay. Then nitrogen dioxide and other NOx gases are important because they are the major contributor to the air pollutions. Okay. So to summarize the gas sensing application for smart building, you have to monitor the indoor air quality as well as you require these gas sensors for leak detection. Okay. It is a demand controlled ventilation, you require these sensors. Okay. Then occupancy based HVAC system, these gas sensors are required, and for of course fire and safety systems, some of these sensors can be essential. Of course, we will discuss the smoke sensor separately because that is an integral part of any smart building, but then some of the gases, for example, if the concentration level of CO2 is going high inside indoor conditions, okay, in that case you can expect that there is a certain case of fire or something else. Okay. So certain gases of course tell you about the fire and safety systems. Okay. So these sensors, all these smart buildings are well equipped with all these sensors. Okay. There are certainly various advantages of using this gas sensor. For example, it helps in improving health and productivity. Then it helps in automating the safety systems. Okay. It makes the HVAC control system energy efficient, and it helps in getting real time air quality data and analytics. Okay. However, these sensors, all these sensors have certain limitations. We have also seen in the module 5, like they can have cross sensitivity and drift, particularly if they are low cost semiconducting sensors. They require calibrations frequently. The sensor's lifespan and the shelf life also is not very high and require frequent replacement. Of course, for optical sensors there are certain assumptions. Okay. Then you have a cost versus performance trade off. So if you pay more, you get better sensor in the form of optical and other devices, but if you compromise on that, you have the low cost sensors, but then you have to compromise on the sensing parameters like limit of detection, sensitivity, repeatability, that kind of things. Okay. Then another kind of devices which are very much essential for a smart building application are particulate matter sensor or PM sensor. Okay. So the particulate matter PM includes various things, including the dust, smoke, pollen, etc. This PM is harmful to the respiratory health, especially the PM 2.5 and PM 10. Okay. Smart buildings use PM sensors for real time air quality monitoring and HVAC control. Okay. If I talk about this particulate matter, it is basically a mixture of extremely small particles of liquid droplets, small particles as well as the liquid droplets in the air. Of course, these small particles include all these things that I have just talked about, the dust, smoke and pollen. Okay. These particles also include some other things like soot, dirt and other things. Of course, they are classified based on their sizes. Like if you have PM10 means the particle sizes are around less than 10 micron. The example can be a dust and pollen. Okay. PM 2.5 include any particles which are less than 2.5 micron size and include some combustible particle, smoke, etc. Then another kind of particulate matter is PM1, which is having size less than a micron, and these are known as ultrafine particles. Okay. So these PM particulate matter, if a person is exposed to this particulate matter regularly inside a building, okay, it can have various hazards on that particular person depending on how much exposure he has with the PM. Okay. If he has a short term exposure to particulate matter, it can worsen his asthma or chronic bronchitis if he is suffering from all these two diseases. Okay. Even in a normal person, it can cause respiratory issues. It can create irritation of the airways, coughing, and it can also cause difficulty in breathing. Okay, it can also lead to non-fatal heart attacks and irregular heartbeats. Okay, for a shorter exposure to particulate matters, it can result in reduced lung function, especially in children and those with pre-existing heart or lung diseases. However, long-term exposure to particulate matters are actually should be avoided. Okay, it can have a risk on heart diseases, and it can even lead to stroke. Okay, it can develop asthma even in children. Okay, it reduces lung growth in children as well as in grown up child or teenagers. Okay, if you are exposed to this this particulate matter regularly, there is a likelihood of developing diabetes. Okay, impaired cognitive function and neurological effects are another thing which this PM can cause. Okay, then premature death in people with heart or lung conditions has been reported clinically by this particulate matter. Okay, so the detection of this particulate matter in precise level is very crucial. Okay, so there are different type of particulate matter sensors, like optical PM sensors, which are very popular. They are basically based on reflection technique or scattering techniques. Okay, of course there can be multiple sources. It can be based on laser, it can be based on some other light source. Okay, you have gravimetric PM sensors, you have beta attenuation monitoring or BM particulate matter sensor. Okay, you have electrostatic PM sensors also, and then very popular MEMS based PM sensor. Okay, so these 5 type of particulate matter sensors actually dominate the market. Of course, the lead is taken by the optical PM sensors. Okay, so what we will do is in the next class, or which will be essentially our 5th lecture in this module, we will discuss some of them, and then we will talk about the smoke sensor in continuation. Thank you.